So we're here doing some mechanics today. We're going to be looking at question 1 of the 2008 AP Physics C Mechanics exam. It's the free response question. And what we have here is a skier of some unknown mass, big M, skiing down a frictionless hill that makes an angle theta with the horizontal, as shown in the picture up here. The skier starts from rest at time 0 and is subject to a velocity-dependent air force. So it's a drag force going on there. And it's of the form F equals minus BV. The minus there due to the fact that it is opposing the skier. The B is just some constant. Normally these are for air drag forces based off of the cross section of the object that's moving, dependent on how much, what density of the air you're in, which is actually dependent on your altitude and blah, whatever. And then the velocity. And we just have a minus BV here instead of like a minus BV squared, which is a little bit more true. And V is the velocity of the skier, B is a positive constant. Express all algebraic answers in terms of M, B, theta, and the fundamental constants, whatever those are. So let's get into this. What we're asked to do in part A is to just draw a free body diagram of the skier, indicating and labeling all the forces that act on the skier while they're descending the hill. Now, remember, when you're drawing a free body diagram, do not draw the vector components, okay? And I'll show you what I mean by that in a second. What we should be drawing here is this skier, because they have mass and they're in a gravitational field here on Earth, they have a weight, okay? So we can draw a weight in here, and that weight, as you remember, is equal to a mass times gravity, okay? So weight is something that exists. They also have, because the hill is supporting them, they have a normal force pushing against them. And remember, it's called a normal force because it's always perpendicular to the hill surface. I do my best to draw the normal force there. And our last force we have is the actual air drag pushing against everything there. So our air force, that drag force, just goes here. It is some force here, F. What you should not be doing, and don't do this. You want to do this, but don't. If you were to draw a force going here, which is the mg sine theta term, that's the force pulling down the hill, you're going to get this wrong, okay? You're not allowed to put that in a free body diagram. That is not a force, that is a component of the force. So what we have right here, that's it. That's everything. You're done, okay? Do not put extra vectors in there. Do not break these vectors up into their components. That is not what they want you to do here. A free body diagram is just asking what are the vectors, or what are the forces, what are the force vectors currently acting on the object, okay? So that's it. 3 vectors there, the weight pulling you down, the normal force pushing against the surface, and then the frictional force, that air drag, pulling you back, okay? So now that we've gotten that easy 3 points out of the way, and that was 3 points there just for labeling those 3 vectors. Now we've got to start writing differential equations. And this gets back into our F equals ma. Anytime you see differential equation for a force problem like this, you know that you are going back to F equals ma, okay? So what we need to start here is we just want to start off by writing F equals ma here, and then start running from there. So we know that F net equals the mass of the skier times some acceleration. And I guess if that's the mass of the skier, we should really write that as big M in this problem here, okay? At this point, we need to start looking at what forces do we have here, what's going on here, okay? So this net force that we have is actually a combination of 2 forces. It is a combination of the weight pulling down the plane and the friction pulling back. So we know that this weight component is going to act down the plane in an mg sine theta term. And then we know that this force, F equals minus BV, is going to pull back. So what we have for F net here is we could write this, if we take down the plane as being positive and up being negative, we can say that mg sine of theta, or I guess once again M is a capital M, because so it's the mass of our skier, minus this force of friction, BV, equals the mass of the skier multiplied by their acceleration, okay? The only thing we need to do in order to turn this into a differential equation is to recognize what this acceleration is. If we plot a velocity graph, we see that the acceleration is the slope of that graph. So this acceleration here, and this is true anytime we see a differential equation with forces, that acceleration vector is going to equal dv dt. This is just a slope, okay? This is how in calculus we write slope dv dt as a function of time. So what we're just going to do is we're going to take this dv dt and we're just going to throw it in right there for the acceleration. So whoosh, wipe it, dv dt. And that's it. Right there, that is a differential equation. Okay, so right there, you've just gotten another 4 points for having this differential equation. You have F equals ma, you have mg sine theta, you have bv, and it's negative because it's opposing the direction. And we've substituted in the dv dt for what's going on there. Okay, so that's what's going on in this problem. The only thing we really needed was this dv dt, pretty straightforward. Okay, now in part C, we need to determine an expression for the terminal velocity of the skier. And this word terminal velocity here is really nice because whenever you reach a terminal velocity, your F net equals 0. You're not speeding up anymore. You're not slowing down either. You're just coasting at a regular velocity that is not changing. So what this means is that F net equals 0. This equals mg sine of theta minus bv, where once again this is the mass of the skier, big M. And that means that I just need to solve this equation for v and call it a day. So if I add bv over, I'm going to get bv equals mg sine of theta. And then if I divide each side by b so that the b's divide out and they cancel, we see that v is equal to mg sine of theta divided by b. And boom, that's it. The big takeaway here is that terminal velocities are F net equals 0, and we already wrote an expression for F net above. If you don't know if you got part B correctly with that differential, and you're like, oh, I don't know, what's going on? Use whatever you had before and just take it through, okay? Just use it again. You'll get continuity points here, okay? You'll get continuity points for what's going on, but that's an easy 2 points there. So at this point, you've picked up 3 from part A, another 4 from part B, so we're at 7, and then part C here, in easy algebra, that's 9 points. You just scored 9 out of 15 points on this question. Part D here, this is the big differential solving that you have to do. This is where the calculus starts coming in. This is only worth 3 points. So if you're not very familiar with your calculus, or you're like, I'm not sure if I'm doing this right, do not waste time here. If you are wasting time here, if you're like, oh, I don't know what's going on, oh, I'm hoping I'm doing this right, just move on. Okay, go to the second question you've got, go to the third question you've got. Don't waste your time here. Okay? If you feel really comfortable with your calculus, great. Stick around here, do some of this, but if you don't, just move on. Okay? In fact, let's just move on to part E real quick, and then we'll come back to this just to see that we can do this. Okay? In part E, we're asked to sketch a graph of the acceleration of the skier as a function of time and indicate the initial value of A, taking downhill to be positive. Okay? Well, if we start somewhere, we know just based off of the skier, because the air resistance is pushing against them, we know that their acceleration will slow down. Eventually, as we saw here, they're going to hit a terminal velocity, and that acceleration is going to be 0. So we know that this graph needs to end low, and it needs to start up high. The question just becomes, does it go down in a straight line, does it curve like this, or does it curve like this? Because we know it's not going to do anything weird like that, okay? So in terms of that question, we know that as the person is sliding faster down the hill, there's going to be more and more more and more of a force pushing against them, so their acceleration is going to drop more and more. So what we're going to see is, since that more and more feature exists, we're going to get a curve here, and it's going to curve like this, okay? It's going to reach concave up there. This concave, this curve is pointing up, okay? So right there, we just got a point for having it go concave up. Technically, we're never going to reach this x-axis here. We're never going to reach a value of 0, and the reason being is because as we move faster and faster, more force is going to be pushing against us, but we're never going to reach it. We're always going to be speeding up just the tiniest bit. So we got another point for just making sure that we went aligned with this x-axis. We never reach 0. We've got an asymptote here, so that's a point there. So we just got 2 out of 3 points for this problem, and the only last thing we need to do is label an initial value of A, which we know that as well. If we go back up to the very beginning here, where we started writing our force equations, well, if we're not moving yet, then this is what we had, but V would equal 0. So what we could say here for our value of A is, if we have mg sine theta minus 0, because BV equals 0, V is 0 there, that equals MA. And that means our m's divide out, which means that this initial starting point is g sine theta. So right there, we just got 3 points for that by drawing a curve, didn't hit the x-axis, and we knew just from our F equals MA equation what that initial point had to be. So right there, without doing any calculus, we just got 12 out of 15 points on this question. You can move on, rip it to the next one, and go, 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 go. If you want to do the calculus, though, let's solve this differential. The differential equation we had from before was, and I'm going to write it like this, m dv dt equals mg sine theta minus bv. Now, when we want to solve these differential equations, we're going to separate our variables here, which means that I'm trying to get everything with v's in them on the same side, and anything with t's in them to a side amongst themselves. Now, the issue comes is that since this is a subtraction problem here, this mg sine theta minus bv, this all has to stay together, which is going to make this look a little ugly, but it is what it is, okay? I'm going to divide the mg sine theta minus bv over to the left side, and I'm going to multiply and bring over to the right side the dv and then divide by the m to bring that over and that over. So the way this is going to look is I'm going to have my dv, it stayed, divided by the entire ugly big term. Mg sine theta minus bv equals dt over m. Okay, that's where I'm beginning. From just placing this right here like that, I've just gotten a point. Okay, there's only 2 more points to get in this problem, so like I said, if you're struggling here, move on. What we need to do now is we need to solve this integral, or solve this differential, by using an integral. So what we're going to do is we're going to integrate each side here, and I'm going to integrate my time from 0, the initial time, to some time later, t, and I'm going to integrate my velocities from the initial velocity, which was 0, to some velocity at some time later, which will just be vt. Okay? So at this point, this right side here is actually a very straightforward integral. This m in the denominator is a constant, so it actually gets pulled out. We could write this integral, and I'm just going to do these to the side, as 1 over m by the integral 0 to t dt. When you integrate just the dt term, it just comes back as t. So we're going to get 1 over m times the quantity t from 0 to t, placing in my upper minus lower terms, gives us an answer here of just t over m. Okay, so that was very straightforward for the right side. The left side is a little bit more challenging. To do the left side here, we actually need to do a u substitution. So for a u substitution, what I've recognized is I've got a dv in the upper term and a v in the lower term. So I know I'm going to get a natural log out of this, but I've got all this other junk here that I also need to deal with. So what I'll do is I'll create a term u, and u is going to be mg sine of theta minus bv. And then what I'm going to do is I'm going to take the derivative of this new placeholder variable u. So the derivative of u is going to equal, and then I need to take the derivative of this term here. Okay, and I'm actually going to take this specifically with respect to v. So this is going to look like, well, mg sine theta doesn't have a v term in it, so that's just a constant. Derivative of a constant is 0. Minus, well, minus bv. I have a v term in there, that's like v to the first, so I'm going to have minus 1b v to the 0, which is 1, so I'm just going to get minus b here. And 0 minus b is just minus b. And then I'm going to bring this dv over to this side. So what I'm going to see is du is equal to minus b dv. Okay? What this allows me to do here is, hey, if I look up here, I have a dv term. All I need to do is get a minus b into that numerator. Well, the way we get the minus b into the numerator here is we'll multiply by 1. Let's multiply by minus b over minus b. By doing that, I can link these together, and then I can keep that minus b as a constant just separate to the outside. So what this integral is going to look like over here is it's going to be the integral from 0 to vt. I'm going to have a 1 over minus b on the outside because I need to keep that term there. And then I'm going to have du over u. And technically, if you're into math and whatnot, we should have replaced this bound right here. I like shifting everything back out of the u term once I'm done with it, so that's why I don't do that. But if you like doing that, like, so be it, do your thing. But when we integrate this, what we're going to see is the integral of du over u, or integral of dx over x, or whatever variable you have, is a natural log. So what we're going to get here is minus 1 over b natural log of u, and then our bounds, which we have. And what I like to do is I like to write this as minus 1 over b natural log of, and then I like to dump my u term back in. And my u term was mg sine of theta minus bv. And then I like to bound that from my 0 to v of t. Okay, and remember, this was all equal to t over m. And what I'm going to do to make my life a little bit easier here, and a little neat trick here, I'm going to take this minus 1 over b, I'm going to bring it over to the other side. So it's going to be a minus bt over m. So now I can look at this. I've done the hard integration, I've done my u substitution. Now I need to get a nice little answer for us here. So what I can do is I can start looking at plugging in my upper bounds and lower bounds in for v. And when I do this, and let's just keep everything nice and neat here, I still have my minus bt over m equals, well, if I plug my upper bound in, I'm going to get the natural log of mg sine of theta minus b v of t, and then minus the natural log of mg sine of theta minus 0, because when I put that 0 in for v, that becomes nothing. Well, if we remember back to our log rules, we see that when we're subtracting logs, we're actually dividing. So what we can do here is we can rewrite this as minus bt over m equals the natural log of mg sine of theta minus b v of t over mg sine of theta. Okay? So that's where we're at now. We used the log rule to get into this. And as you do more and more of these integrals, you'll see more and more of these same setups happen again and again and again as to what's going on here. So this isn't kind of new for us or anything like that. What we can do at this point is to get rid of this natural log, we exponentiate each side. When we do that, the natural log goes away. So we get e to the minus bt over m equals mg sine of theta minus b vt all over mg sine of theta. And you can see my starting to work fast here because I realize we're close to the end. What we can do here is we can recognize that these terms are the exact same, so we can write this as a 1 minus, or what you can do is, and there's a lot of ways you can solve out the algebra from this point. It's really up to you. But what we're going to see in the end, I'm just going to write it. I'm just going to multiply the, how do I want to do this for you? I'm going to multiply the mg sine theta over here just to make life how I like it. And what we're going to see here is we're going to get mg sine of theta e to the minus bt over m equals mg sine theta minus b v of t. Woof. And then I am actually going to take the minus b v of t, and I'm going to sling it here, and then take this and sling it back to the other side, just because I like how it looks. I think it looks a little bit nicer for me. So I'm going to get b v of t equals, and then this is going to be mg sine of theta minus mg sine of theta e to the minus bt over m. And then this is the last little cleanup move here. Noticing that these are the same, I'm going to factor out the mg sine of theta, and then I just need to get rid of this b term here, so I'm going to divide by it in the end. So what I get here is that v of t equals, here's my factored out term, mg sine of theta, and then that's going to be multiplied by 1 minus e to the minus bt over m, and then I just need to make sure I've divided by my b. And that's it. That's solving for the differential equation. So all of that math there at the end, that long, arduous math step, that was a point, which that stinks, right? So if you're taking this test and you're like, I don't know what the heck you just did there, I'm not super good with my math, or hey, I understood that, but it took me a little bit of time, know that, just skip it, okay? Don't need to get a perfect on this test. If you can get 12 out of the 15 points that we talked about in the beginning, parts A, B, C, and E, great. If you want to get this exponential decay term of the velocity and how it reaches some point, or rather, not an exponential decay, but a growth reaching some point, then you can do that, but you don't need to, okay? So this velocity is going to grow with time. As time reaches some infinity term, so if time equals infinity here, then this essentially becomes 0, and this actually becomes the maximum speed that we have. So that's kind of interesting there too. So there's some other problems that take a very similar look at that. Sometimes you'll see that question, sometimes you won't, but that is the max speed right there that you're going to have at time equals infinity going down this very, very long hill. So I hope you enjoyed this problem. There was kind of a lot to it, and we kind of went off the deep end of the math to get that differential equation done, but beginning of it was much easier. Draw your free body diagram, set up this differential equation with the dv dt, set f net equal to 0 to find a terminal velocity. We know we're going to have a concave up curve with g sine theta is equaling our initial acceleration when the velocity is 0, and then all of the math, okay? But with all of that done, this problem is finished. Hope you enjoyed it. Adios.